welcome back to the deep dive. If you're preparing for a system design interview, whether it's for that mid-level promotion or maybe a senior role at a big tech company, you know that feeling. The clock,
Oh, that clock is terrifying.
it's just ticking down. You have, 45 minutes, maybe an hour to sketch out this huge scalable architecture for, I don't know, a global video streaming service.
Or a payment processor, something with zero room for error.
Exactly. It feels like you're doing technical triage, just trying to prioritize under this immense pressure.
It absolutely is. And, the sources we've been looking at for this deep dive, they all really focus on one thing: structure.
Structure, okay.
Because, and this is the key thing, the reason so many really sharp candidates fail these interviews, it's not because they don't know the tech.
Right. It's not a knowledge gap.
Not at all. It's a lack of a proven strategy,
Yeah.
a way to actually deploy all that knowledge in the very limited time you have.
So that's what we're going to talk about today. We're giving you that structure.
We are. We're going to lay out what we're calling the system design delivery framework. And then we're going to dive right into the pillars of that framework. We're talking API design, the API gateway, and of course, data persistence strategies.
Okay, let's unpack that point about structure, because I think it's so important. So many people, you see them go into these interviews and they just rush straight for the cool tech.
Yep. Straight to the database choices, the caching layers.
But they haven't even really defined the problem they're trying to solve.
Yeah.
So why is following a framework like this? Why is it the secret weapon?
Well, it forces you into a linear, kind of accountable thought process. You have to prove, while you're under all that stress, that you can go from a really vague idea, like design a short video app.
Which is a classic one.
It's a classic, right? And you have to turn that into a concrete, deployable plan. The framework just makes sure you hit the critical first steps quickly.
So you're not wasting time.
Exactly. So you leave the most valuable time, maybe 10, 15 minutes at the end, for the architectural deep dives. And that's where the senior level talent really shows.
That's where you're actually measured.
That's it. If you skip steps, you will inevitably have to backtrack. And that just kills your time budget.
So, okay, let's outline it. This delivery framework you're recommending, where does the clock start? What's step one?
The first, say, 5 to 7 minutes are maybe the most critical. Step one is requirements.
Gathering requirements.
But you're not just gathering them. You are, in a sense, interviewing the interviewer. You have to clarify the functional requirements. So what must the system actually do? Upload a video, post a comment, that kind of thing.
The features.
The features, yes. And then, crucially, the non-functional requirements. What must the system withstand? We're talking latency targets, availability numbers, and, of course, scale.
Yeah, you really have to negotiate those numbers, right? It's not just a given.
You have to, because they dictate every single technical choice you make later. For example, are we talking about 99.9% availability, 3 nines?
Or the famous 5 nines.
Or the 5 nines, 99.999%. The difference between those two is a massive, massive jump in complexity and cost. You have to clarify that up front.
That makes perfect sense. You establish the contract before you start building. So what's the rapid-fire second step?
Step 2 is to define your core entities. These are basically the nouns of your system.
The nouns.
The nouns. The objects that will eventually map pretty closely to your database tables. So for that video app, it's simple. User, video, comment, like.
Okay.
Getting those down on the whiteboard early gives you immediate context for the next phase.
Which takes us to step 3, defining the API, the contract itself.
Precisely. This is where you define how the outside world, the mobile app, the web browser, is going to talk to your backend.
Okay, so you've got requirements, entities, API. What's next?
Once that API contract is set, step 4 is to sketch the high-level design. This is the classic boxes and arrows diagram that everyone thinks of.
Right.
You're just showing the basic services. You'll have an authentication service, a video processing service, a database. This part is all about proving you can meet the core functional requirements.
And now, the part everyone seems to run out of time for.
The payoff.
The payoff. The final and the biggest phase, the deep dive. This is where you come back to those non-functional requirements.
The scale, the latency.
All of it. You're answering the hard questions now. How do we handle 3 billion reads per day? How do we guarantee strong consistency for a financial transaction?
So this is where you talk sharding, caching.
This is where you bring out the big guns. Database sharding, caching strategies, asynchronous processing with message queues, specialized storage. If you rush the first few steps, you just won't have time to show your depth here. Which brings us back to that time management tip that all our sources really emphasize. You've got to get through requirements, entities, and the API design in what, 10 or 12 minutes total?
Something like that, yes. And the API part in particular needs to be lightning fast.
Why the strict 5-minute limit on just designing the API? It seems so important.
It is important, but the interviewer just needs to see a reasonable path forward. They don't need a perfect, exhaustive API spec.
They're not looking for perfection.
No, they're testing if you understand the standard conventions, like resource modeling. They really don't want to spend 10 minutes debating whether the API version goes in the URL path, like v1, or in a header.
Just make a reasonable choice and move on.
Make a choice, justify it briefly, define the 3 or 4 most critical endpoints, and move on to the architecture. Dive.
Excellent. Okay, that's a perfect transition. Let's move into that API layer itself. This is the foundation of that external contract. We've basically got 3 main protocols to choose from: REST, GraphQL, and gRPC. What's the safe, reliable default here?
For, I'd say, 90% of user-facing systems, so anything that's going to be hit by a web browser or a mobile app, the default is REST, representational state transfer.
And why is that?
It's mature, it's relatively simple, it uses the standard HTTP verbs that everyone knows: get, post, put, delete, and the tooling and library support is just universal.
So unless there's a really compelling reason not to, you start with REST.
You always start your answer with REST unless the requirements from step 1 explicitly push you in another direction.
Okay, sticking with REST then. The core principle you mentioned is resource modeling. You said resources have to be plural nouns, not actions or verbs. Can you break that down a bit more? Why is that distinction so critical?
It's all about creating a predictable, almost intuitive interface. A good RESTful endpoint should feel like you're just navigating a file system.
Okay, I like that analogy.
So if you're building an API for a music service, your resource is tracks. It's plural. It's a noun. You don't create an endpoint called fetch track BAD or delete song.
Because those are actions.
Exactly. Instead, you use the standard HTTP verbs on that plural noun resource. Get ttracks 123 fetches that specific track. Post tracks creates a new one. Delete tracks 123 deletes it.
And that clear noun-based structure just makes the whole thing easier to understand and use.
It makes it self-documenting, in a way, and much easier to scale and maintain.
Okay, that structural clarity is key. Now let's get into the mechanics of actually passing data. There are 3 main ways: path parameters, query parameters, and the request body. I think a lot of people get mixed up, especially between path and query params.
That's a super common point of confusion, but the distinction is actually very clear, and it's all based on necessity.
Necessity.
Path parameters are part of the resource's unique identifier. They are absolutely required for the request to even make sense. So if you're getting track ID 123, the path is tracks. That ID is an integral part of the path.
The request is meaningless without it.
Precisely. Now, query parameters, on the other hand, are optional modifiers. They're used for things like filtering, sorting, or pagination.
So they come after the question mark.
Exactly. They follow the main resource path. For instance, you might want all tracks released in 2023. That would be tracks.year 2023. Maybe you want to filter more, and genre pop and sort release date.
And the original request, just tracks, is still perfectly valid on its own.
It is. The query parameters just refine the collection you get back. They're also perfect for things like pagination, like .limit50 in cursor, ABC.
Okay, so if the data is required to identify the specific item, it's the path. If it's optional and used to filter or manipulate a list, it's the query. So where does the request body fit in?
The request body is for the heavy lifting. It's for the complex data payload.
So not for the URL.
Definitely not. You use it with POST, PUT, or PayTCH request. Think about creating a new user. You're not going to put their password, their address, their user preferences, all of that into a long URL string.
That would be a security nightmare, for one.
A huge one. So you bundle all of that complex information, probably as a JSON object, into the request body. It's essential for any data that's large, has many fields, or is in any way sensitive.
This brings us to a really critical concept, something that I feel like always comes up in these interviews: idempotency. It shows you're thinking about network instability. So can you explain why idempotency is basically our shield against flaky networks?
Right. So in any distributed system, you have to assume failure is normal.
Things will break.
Things will break, network connections will drop, servers will time out, and clients are usually programmed to automatically retry a request if they don't get a clear success response back.
Okay.
Idempotency is the property that ensures if a client sends the same request multiple times, the outcome is the same as if it had sent it only once.
So retries don't cause unintended side effects.
Exactly. It prevents you from, charging your credit card twice. Think about a GT request. It's naturally idempotent. You can ask for a user's profile 10 times. You still just get the same profile back. You haven't changed anything on the server.
Makes sense. What about delete?
Delete is also idempotent. If you call delete users 1, 2, 3, the first time it deletes the user, the second, third, and fourth times. Well, the user is already gone. So the end state of the system, the user being deleted, is the same.
And PUT, since that's for a full replacement of a resource.
PUT is idempotent, and this is a key point because you're submitting the entire state of the resource. If I put a user profile with the name Alice and the network drops, so my client retries, the second PUT will just overwrite the resource with Alice again. The final state is always just Alice.
Okay, but then there's the big one, the one that causes all the trouble. Post. This is the system design troublemaker.
Yeah.
If PUST is non-idempotent and we know clients are going to retry, what's the mitigation strategy?
So the fundamental problem with PPOS is that every single call is designed to create a new resource.
A new thing every time.
Every time. So if you post a new flight booking and the client retries because of a timeout, you now have 2 flight bookings. That's a huge problem.
Like, what do you do?
The most common and the most robust mitigation strategy is to require the client to generate and pass a unique identifier in the request header. It's often called an idempotency key or a client request ID.
An idempotency key.
Okay. The backend server gets this request, it pulls out that key, and the first thing it does is check a fast key value store, like Redis.
It looks it up.
It looks it up. If it sees that idempotency key has already been processed successfully, it doesn't run any of the business logic again. It just immediately returns the original success response that it saved from the first time.
So it fakes the success.
It's not faking it, it's confirming the original success. But if the key is new, then it goes ahead, executes the transaction, saves the result, and then records that idempotency key as completed in Redis.
Ah, so you're effectively making a non-idempotent POST act like an idempotent one, at least for the purpose of retries.
You are. And explaining that pattern is a huge signal of seniority in an interview.
Yeah.
It shows you're thinking about real-world failure modes.
That's a fantastic, detailed example. Okay, let's pivot to the alternatives. When do the system requirements tell us, okay, REST isn't the right tool here, we need to choose GraphQL?
The signal for GraphQL almost every time is about complexity on the front end. It's about having diverse clients like a mobile app and a web app with very different data needs.
Different needs, okay.
And it's about solving the problem of data efficiency. With REST, the server decides what the data payload looks like, and the client is forced to accept it. This leads to 2 classic problems.
Which are?
First is overfetching. The mobile app might only need the user's name and their avatar, but the user's REST endpoint returns 50 different fields. That's just wasted bandwidth, which is a killer for mobile performance.
Wasted data, slower load times. And the second problem?
Underfetching. To build a single complex screen like a user's profile, the client might have to make a chain of requests. First, get the user details. Then, get their last 3 orders. Then, get their recent comments.
A waterfall of network requests.
Exactly. And each one adds latency. GraphQL solves both of these by flipping the control. The client specifies the exact shape of the data it needs in a single query to a single endpoint.
But this incredible flexibility comes with a very famous trade-off, right? The notorious N+1 query problem. Can you explain that and then walk us through how the standard fix, the data loader pattern, actually works?
Yes, the N+1 problem is the big gotcha with GraphQL. It happens because a single GraphQL query can, walk across relationships in your data model.
Right.
So let's use an example. A client asks for a list of 100 blog posts. And for each of those posts, it also asks for the author's full profile.
Okay, so 100 posts and the author for each one.
Without any optimization, the GraphQL resolver logic on the back end might do this very naively. It'll run one query to get the 100 posts.
That's the one.
That's the one. Then it will loop through those 100 posts, and for each one, it will trigger a separate database query to fetch the author details for that post.
And there's the N, the 100.
There's the N. So one GraphQL query results in 101 database lookups, and that will just crush your database connection pool. It doesn't scale.
So the data loader, how does it fix this?
The data loader pattern is basically a smart, short-lived caching and batching layer that sits between your GraphQL server and your database.
Okay, a batching layer.
So when those 100 different resolvers all ask for an author ID, the data loader doesn't hit the database immediately. It's smarter than that. It just collects all of those author IDs that are being requested within a single tick of the server's event loop.
It gathers them all up.
It gathers them all up. Then, once that tick is over, the data loader executes one single combined query to the database. Something like select from authors where id in, ID1, IV2, all the way to ID 100.
So it turns 100 queries into one.
Exactly. It gets all the results back in one efficient network trip. Then it uses an internal map to distribute the correct author back to each of the original 100 resolvers that asked for it. It's a fundamental optimization for GraphQL.
That is a much more detailed answer than just saying use batching. That's
Yeah.
the level of detail you need. Okay, finally, let's touch on the third option, gRPC, or RPC in general. Where does this fit in the picture?
gRPC is the protocol for your internal architecture. It's for the hallways of your system, not the front door.
So not for public clients.
No, you would almost never expose a gRPC endpoint directly to a web browser. It's designed for extremely high-performance machine-to-machine communication, especially in a microservices environment.
And why is it so much faster than, say, JSON over REST?
Two big reasons. First, gRPC uses something called protocol buffers, or protobuf, for serialization.
Instead of JSON.
Right. JSON is text, it's human readable. Protobuf is a binary format. It's much smaller on the wire and significantly faster for a machine to encode and decode. That means less latency, less bandwidth.
Okay, so binary format is one. What's the second?
The second is that gRPC is built on top of HTTP2. And HTTP2 has some major advantages over the HTTP 1.1 that traditional REST uses. The biggest one is multiplexing.
Multiplexing.
It allows you to send multiple concurrent requests and responses over a single TCP connection without one slow request blocking all the others. This is huge for high throughput scenarios where microservices are constantly chattering back and forth.
Okay, so the rule of thumb is REST for the front door, gRPC for the internal hallways. That's a perfect way to think about it. And a great transition to Section 3, securing and directing traffic with the API gateway.
The API gateway. It's become really the central nervous system of any modern system. It's pretty much a mandatory component if you're building with microservices.
So what is its fundamental role?
Its role is actually very simple in concept. It is the single entry point for all external client traffic. All requests from the outside world go through the gateway first.
Why is that considered a key technology and not just, another service in the diagram?
Because it centralizes all of the boilerplate, cross-cutting concerns that you don't want every single one of your microservices to have to worry about.
Can you give an example?
Sure. If your booking service also has to implement its own rate limiting, its own authentication logic, its own logging, it gets distracted from its core business logic, which is just handling bookings. The gateway offloads all of that generic work.
So it lets the services focus on what they're good at.
Yeah.
Let's detail those core functions then, starting with just directing traffic.
Request routing is the absolute foundation. The gateway looks at the incoming request path, say OP of users, and it uses that information to intelligently route the request to the correct backend service.
So it's like a smart reverse proxy.
That's exactly what it is. It insulates the client from the complexity of where your services actually live. The client just knows one address, the gateway's address.
Okay, the second function, and you could argue it's the most critical, is security.
Absolutely. Authentication and authorization. The gateway is the bouncer at the club.
I like that.
It intercepts the client's request, looks for a security token, a JWT, for example, and it validates it.
Yeah.
It checks the signature, makes sure it hasn't expired, and figures out the user's identity and what they're allowed to do.
And only then does it let the request through.
Right. And once it's validated, the gateway often injects the user's ID and maybe their permissions directly into a header before forwarding the request. That way, the downstream services can just trust that the request is authentic.
That seems like a huge performance gain. If every single microservice had to go hit a database to validate a token, the whole system would grind to a halt.
It would be incredibly inefficient. The gateway centralizes that check, which leads to the third critical function, rate limiting.
Protecting the backend?
Protecting the backend services from just getting overwhelmed. Whether it's a sudden, legitimate traffic spike or a malicious denial of service attack, the gateway is the first line of defense.
And how does it do that?
It implements throttling rules. It can be based on the user's IP address, their user ID, their API key. To keep track of this, it usually uses a very fast distributed data store like Redis
To count the requests.
to count the requests within a certain time window. It uses algorithms like the token bucket or leaky bucket to enforce those limits fairly and prevent sudden bursts from taking down the whole system.
Okay, and the last function kind of ties back to our protocol discussion. Protocol translation.
Right. The gateway is the bridge. It can accept that public-friendly REST request with JSON from a mobile app, but before it forwards it to the internal user service, which we designed to use high-performance gRPC, it can automatically translate that HTTP request into a binary protobuf request.
So you get the best of both worlds.
You do. Clients use familiar protocols, while your internal architecture gets all the speed benefits of gRPC.
Let's dig into the security mechanisms a bit more. When should we be choosing JWTs, JSON Web Tokens, versus, say, simple API keys?
JWT is the modern standard for user sessions, so anytime a human being is logged into your web app or your mobile app.
And what makes them so popular?
The big advantage is that they are stateless. The token itself contains all the information you need, the user's ID, when it expires, maybe their roles, and it's all cryptographically signed.
So the gateway doesn't need to check a database.
Exactly. The gateway can verify the signature using a public key it has in memory. It proves the token wasn't tampered with, all without a slow network round trip to a session database. That stateless nature is absolutely essential for scaling.
But there's a well-known drawback to JWTs, isn't there? Because they're stateless, how do you revoke one? Like if a user logs out or their account is compromised, how do you kill that token immediately?
That is the key trade-off, and it's a great interview question. Since the token is valid until its expiration time, you can't just delete it from a database.
What's the solution?
The common solution is to maintain a revocation list, often in a fast store like Redis. But if you check that list on every single request, you've just lost your stateless performance benefit.
You're back to making a network call every time.
You are. So the more robust pattern is to use very short-lived access tokens, say they only last for 15 minutes, and you couple that with a long-lived single-use refresh token.
A refresh token.
Right. The refresh token is stored in a database, and its only job is to be exchanged for a new 15-minute access token. If a user logs out or you detect a breach, you just revoke the refresh token in the database. The old access token will just expire on its own in a few minutes.
That's a very complete answer. So what about API keys then?
API keys are for a different use case. They're for programmatic server-to-server communication, or when you're giving access to a trusted third-party developer, like the Stripe API.
So they authenticate a machine, not a person.
Exactly. They're authenticating an application. And because they're typically used less frequently than human user sessions, it's more acceptable for the gateway to do a quick database or cache lookup to validate the key and fetch its associated permission.
And what about scaling the gateway itself? Does it become a bottleneck?
It can, but it's designed not to. Because the gateway itself is meant to be stateless, it offloads session state via JWTs or to external caches like Redis. It's a perfect candidate for horizontal scaling.
Meaning you just run more of them?
You just run multiple identical instances of the gateway software behind a big public load balancer. Traffic gets spread out evenly, and if you need more capacity, you just add more machines.
Perfect.
No.
Okay, that covers the front door and the traffic hop. Now we get to the heart of any system, how we actually store the data. Section 4, persistence and designing the storage layer. This is where the really hard trade-offs live.
This is probably the most complex part of the interview, for sure. Every choice you make about data modeling has to be grounded in those three factors we mentioned way at the beginning.
Let's repeat them.
Data volume, access patterns, and your consistency requirements. You can't just say, I'll use MongoDB. You have to say, I'll use MongoDB because my data schema is flexible and my primary access pattern is fetching a user's entire document.
So with that in mind, what's the default choice? And when do its guarantees actually become a problem?
The default choice almost always should be a relational database, something like PostgreSQL or MySQL.
The old reliable.
The old reliable. They are fantastic when your data is highly structured, the relationships between entities are clear, and most importantly, you require strong consistency through ACID guarantees.
Okay, let's quickly break down ACID for anyone listening because you're expected to know this cold.
For sure. ACID stands for atomicity, meaning transactions are all or nothing. If one part of a bank transfer fails, the whole thing rolls back.
Okay, C is
Consistency. The database only moves from one valid state to another. It enforces your integrity rules. Isolation means that concurrent transactions don't mess with each other. They appear to run one after the other.
Indeed.
And durability. Once a transaction is committed, it's permanent. It's going to survive a power outage or a server crash.
So relational databases are the go-to for anything that needs to be perfectly correct right now. Financial systems, inventory, booking systems.
Exactly. Anywhere that strong, immediate consistency is completely non-negotiable.
So given that solid foundation, when do we pivot? When do we start looking at the NoSQL alternatives?
You pivot when one of those ACID properties, usually the strict isolation or consistency, becomes a bottleneck at massive scale, or when your data just doesn't fit a rigid schema.
So let's talk about the main types. Document databases, like MongoDB.
You choose a document store when your schema needs to be flexible, or it's changing all the time, or when your data is naturally nested. Think about user preferences. Every user might have a different set of preferences. That's hard to model in a rigid SQL table, but it's trivial in a JSON document.
Okay, what about wide column databases? Things like Cassandra.
Those are for extreme write-heavy workloads at a massive scale. Think time series data from IoT sensors or activity logs or analytics events. You're basically just appending data constantly. They trade query flexibility for just insane write throughput and horizontal scalability.
And finally, the simplest of them all. Key value stores. Redis, DynamoDB.
Right. These are the Ferraris of the database world for a very specific task. You use them when your access pattern is exclusively, get me this thing by its unique key. They're perfect for caching, user session stores, leaderboards, anything that needs lightning fast reads and writes on a simple key lookup.
So the big lesson here seems to be, don't pick the shiny new NoSQL database just because it's trendy.
Please don't. Pick it because your requirements, like needing to handle 1 million writes per second, absolutely demand the specific trade-off that database makes.
Start simple.
Always start with a relational database. You can always shard it later or introduce a specialized NoSQL store for one specific part of your system that needs it. Prematurely choosing a complex NoSQL database can introduce a world of operational pain.
Let's stick with the relational world for a second and talk schema design.
Yeah.
This is the classic battle, normalization versus denormalization.
Right, the battle between data integrity and read performance.
So what is normalization?
Normalization is the purist's approach. You follow the rule that you store each piece of information only once to eliminate redundancy. So a user's name exists in one place and one place only, the user's table.
And the benefit of that is?
It prevents update anomalies. If a user changes their name, you only have to update it in that one spot. The data is always consistent. The cost, however, is that to get a full record, like a blog post with its author's name, you have to perform an expensive join operation at read time.
And joins are slow at scale.
Joins are one of the first things to kill performance at a massive scale, which leads us to denormalization.
The pragmatic approach.
It's the pragmatic approach, driven entirely by read performance. Here, you intentionally duplicate data. You might store the user's name directly on the posts table alongside the post content.
So you avoid the join, the read is super fast.
The read is incredibly fast. But now you have a new problem. What happens when the user updates their name? You have to find every single post they've ever written and update the name there too.
And that introduces the risk of inconsistency. So what's the senior level answer in an interview? How do you approach this?
The senior answer is this. You start with a clean, normalized model and you index it heavily. Then you identify your most critical read path, the one query that gets hit 1 billion times a day, like loading the main social media feed.
Okay.
If that specific query is too slow because of joins, then and only then do you selectively denormalize that particular view. Often you'll put the denormalized data into a dedicated read cache, like Redis, or maybe a separate read-optimized database.
So the source of truth remains normalized and consistent for writes.
Exactly. And you accept eventual consistency for that one super high traffic read path to get the performance you need.
Let's talk about performance optimization beyond just the schema. Indexing. It's the lowest hanging fruit. How do we make sure we're proposing the right indexes?
The indexes you propose must be directly tied back to the API access patterns you defined in Step 3.
It all connects.
It all connects. If you designed an API endpoint that says getEvents.CityAustin, you had better propose creating an index on the city column of the events table.
Because without it,
the database has to do a full table scan. It has to look at every single row in a potentially massive table to find the ones that match Austin. That's incredibly slow. An index, which is usually a B-tree structure, lets the database find those rows in logarithmic time. It's a night and day difference.
Okay, so indexing gets you far. Read replicas can get you further. But eventually, a single database machine just hits a wall. It can't store more data, or it can't handle any more writes. That's when we have to talk about sharding.
Sharding. This is where we get into true distributed systems territory. Sharding is just horizontally partitioning your data across multiple independent database machines.
It's complex, but it's how you scale past the limits of a single server.
It's the only way, really. And the entire success of your sharding strategy hinges on one thing: choosing the right shard key.
The shard key, this is what determines how the data is split up.
It's the rule that decides which machine a piece of data lives on. For a social media app, a very common shard key is userid. You'd run the userid through a hash function, and the output determines that all of user X's data, their profile, their posts, their comments, all lives on, say, shard 5.
And the goal there is to keep related data together on the same machine. Why is that so critical?
To avoid the two great evils of distributed databases: cross-shard joins and cross-shard transactions.
Okay, but what are those?
If a user's post data lives on shard 5, but for some reason their profile data lives on shard 10, then a simple query to get a post with the author's name now requires your application to talk to two different machines. It adds latency, complexity, it's just a mess.
And cross-shard transactions.
Even worse, trying to guarantee atomicity, that all-or-nothing property across two independent machines, is notoriously difficult. It often requires complex protocols like two-phase commit, which are slow and brittle. You want to design your shard key to avoid that at all costs.
But if we shard by userid, we optimize for user-specific queries, but we create a new problem: hot shards. What's a hot shard, and how do we deal with it?
A hot shard is when one of your partitions gets a disproportionate amount of traffic. So imagine we're sharding by userid, and then a major celebrity joins our platform.
Right.
Suddenly, the one shard that holds all of their data is getting millions of reads and writes per minute, while the other 99 shards are just sitting there, mostly idle. That one shard becomes the bottleneck for the entire system.
So how do you mitigate that?
There are a few strategies. You can use algorithms like consistent hashing to distribute keys more evenly. Or, for a known hot entity like a celebrity profile, you might have a special case. You could move their data to its own dedicated, oversized shard, or you could cache their data much, much more aggressively at the application or CDN level.
Okay, and what about queries that aren't user-specific? Like, what are the trending topics across the whole site right now?
That's the primary trade-off of sharding. Those global scatter-gather queries become incredibly expensive. Your application has to send the query to every single shard, wait for all the responses, and then aggregate and sort the results on its own.
That's not going to be fast.
It's terribly slow. The common solution is to not use your primary sharded database for that at all. Instead, you'd feed data from your primary shards in real time into a separate dedicated system that's built for these kinds of queries, like an Elasticsearch cluster.
Okay, so that brings us neatly into the idea of specialized storage, which is our fifth and final section. Dedicated storage and handling large blobs.
Yeah.
Why do we need a separate system for large files? Why can't my powerful sharded PostgreSQL database just handle, I don't know, a 50 millib user video file?
It really comes down to a fundamental mismatch in design goals. Relational databases are optimized for small, structured, transactional data. Their internal architecture is based on organizing data into fixed-size blocks on disk called pages, which are typically 8 kilobytes.
Okay, 8 KB pages.
Now imagine what happens when you try to stuff a 50 megabyte video file, a binary large object, or blob into a database field. That one single record suddenly spans thousands and thousands of those 8 KB pages.
It just bloats everything.
It bloats everything, it destroys your caching efficiency, it puts huge pressure on the server's memory, and it makes simple metadata queries, like just asking for the file size, incredibly slow because the database has to skip over all that useless data.
And I imagine backups become a nightmare.
A total nightmare. Your backups become enormous, and restoration times can go from minutes to many, many hours. It's just the wrong tool for the job.
So the right architecture separates these concerns. The database handles the small, structured metadata, and the big files go somewhere else. Where do they go?
They go into object storage, systems like Amazon S3 or Google Cloud Storage.
And what are these systems built for?
They are built from the ground up to store huge, often static, unstructured files. They're incredibly cheap per gigabyte, they're practically infinitely scalable, and they provide extreme durability.
Oh.
We're talking 11 nines of durability, 99.99999999999%. They achieve this using clever techniques like erasure coding, where they chop up your file and spread redundant pieces across many different servers and even different data centers.
So in this architecture, what does the database actually store?
The database just stores the file's metadata, things like a unique file ID, the user ID of the person who uploaded it, the creation date, the file type, and most importantly, a URL pointer to where the actual file lives in the object store.
Okay, now let's talk about the pattern that really separates a good design from a great one here, the aha moment. Pre-signed URLs. Why is it so important to keep the application server out of the upload path?
The naive, inefficient way to handle a file upload is client uploads a huge video to your application server. Your application server buffers that whole file in memory. Then your application server turns around and uploads that file to the object store.
What's wrong with that?
Your application server, which is probably running on a relatively small machine that's optimized for business logic, is now acting as a giant, expensive bandwidth pipe. If 1,000 people start uploading 4K videos at the same time, your application servers will either crash or their network connections will be completely saturated.
So they become the bottleneck.
A massive bottleneck, and it affects every other user of your service.
So how does the pre-signed URL pattern solve this so elegantly?
The application server's job gets reduced to two very small, very fast actions. First, the client sends a tiny request saying, "Hey, I'd like to upload a video."
It asks for permission.
It asks for permission, and the server responds by securely generating a pre-signed URL. This is basically a temporary, time-limited token that grants the client direct, specific permission to perform one action like an HTTP PUT for an upload on a specific location in the object store.
So the server gives this special URL back to the client.
It does, and then the client uses that URL to upload the video file directly to the infinitely scalable object store, completely bypassing the application server's network.
Ah, so the heavy lifting is offloaded.
Completely. Once the upload is done, the client just sends one last tiny notification back to the application server saying, "I'm done," and the server can then save the final metadata to the database.
That is a massive efficiency gain. It moves the entire bandwidth burden from your compute layer to your storage layer, which is built for it.
Exactly. And there's one last detail here for really, really large files, multi-part uploads.
Why do services like YouTube or Dropbox need this?
Because when you're uploading a file that's, say, 5 gigabytes, the chance of the network connection failing at some point during that long upload is pretty high. If it fails at 4.9 gigabytes, you don't want the user to have to start all over again.
That would be a terrible user experience.
Awful. So multi-part upload solves this. It requires the client to first split the large file into smaller, fixed-size chunks, say 10 megabytes each. The client can then upload these parts one by one, or even in parallel.
Then the object store handles it.
The object store provides an API to manage this process. It accepts each part individually, and, crucially, if one part fails to upload, the client only has to retry that one small chunk. Once all the parts are successfully uploaded, the client sends a final complete request, and the object store stitches all the chunks back together into the single full object on its end.
It adds resilience and can even speed up the upload.
It does. It's essential for any system dealing with massive files.
This has been an incredibly detailed and I think very practical deep dive into the absolute foundations of system architecture. We covered the strategic framework, the API contract, the API gateway as the traffic cop, and the persistence layer, the heart of the system. Let's try and bring it all together in a final summary.
The main takeaway is to have a strategy. Use that delivery framework to manage your time. Default to REST for your external APIs, but know when the requirements like complex client needs or internal performance push you towards GraphQL or gRPC. Use the API gateway for more than just routing. Make it the central point for security, using JWTs for user sessions, and for rate limiting to protect your system.
And for storage.
And for storage, justify every single choice. Default to a relational database for its consistency, but be ready to explain your shard key strategy when you need to scale. And, critically, separate large static files out into dedicated object storage using that pre-signed URL pattern to keep your application servers fast and lean.
You know, what's so fascinating about all of this is that system design at its core isn't really just about picking a tool from a list. It's about managing complexity and understanding trade-offs.
It's about designing a system that you won't hate operating in 2 years.
Exactly. It's about avoiding future operational nightmares.
And that's really the final provocative thought to leave everyone with. When you're faced with a design choice, the best senior level solution is often the simplest one that solves the core bottleneck without introducing three new, even worse problems.
Like with sharding.
Exactly. The really hard part of sharding isn't picking the shard key, it's dealing with the fallout. It's managing eventual consistency across your distributed caches. It's figuring out what to do when you absolutely cannot avoid a cross-shard transaction.
So, as you're looking at your next design challenge, the question you should be asking yourself is,
What elegant pattern, like the data loader for GraphQL or the pre-signed URL for uploads, can I use to offload a huge operational burden from my main application? And maybe more importantly, what key assumption did I just make that introduced an expensive complexity I didn't actually need to solve the problem at hand?
discipline simplicity.
That's the hallmark of senior engineering.
That is a perfect note to end on. Thank you for joining us on the Deep Dive.